Okay, so I think we'll start since it doesn't seem to move a lot. So today on this workshop, I will talk about quantification of single molecule localization microscopy data. So in this case, basically, it means point clouds. It could be point clouds from other kind of microscopy modality or anything. But it's true that I have done that because we are doing a lot of single molecule localization microscopy in the team. So that's really the basic data that I'm handling every day. So I'm part of the team of Jean-Baptiste Barita, the Interdisciplinary Institute for Neuroscience. And it's been roughly a decade that I'm doing stuff for quantification of single molecule localization microscopy data. So in this decade, I've released a couple of software already, which are SR Tesseler and Colloc Tesseler, for which you can find the software freely available on my GitHub. So in the case of SR Tesseler, there is window installer, one-click window installer, and the code source, which is available. I will explain later in the workshop what is SR Tesseler and what is doing. The same for Colloc Tesseler. And in 2019, I released also Colloc Tesseler for colocalization analysis of single molecule localization microscopy data. Again, you can find it on my GitHub. In this case, there is no code source because I didn't have the time to really clean it. And I choose to take a different road, which is basically I released SR Tesseler in 2015 at that time, and that's the way the software is right now still. It means that you could only analyze in 2D and you could only open one dataset at a time. In 2019, I released Colloc Tesseler. In this case, you were able to do 2D and 3D analysis, and you were able to open several datasets, but there were no 3D visualization. And in 2020, it begins really difficult for me to add code to these two software because of I had code that were 10 years that I written 10 years ago. So the architecture was not good, and it was really a nightmare to add stuff because even changing a line of code could require me 20 minutes to compile. So I really decided to go back to zero and to redevelop a complete platform, which is PoCA, Cloud Analyst, because I found that for my software and the ones that were available elsewhere, there were things that were missing, like proper GUI, proper visualization and interaction. And I really put a lot of effort in order to make this software, PoCA, answer all these limitations. And so PoCA is now released. So it's not published yet. We are working on that. It's released. So you can find it on my GitHub. It's beta release, so it's not yet a proper release, but it's working. So must have some bugs still, but it's working pretty well. Code source of this is available. That's why I didn't put the code source of Colloc Tesseler, because in PoCA you have SR Tesseler and Colloc Tesseler and more. And so you can find it on my GitHub. So if you go to GitHub, and my GitHub is F Levet, you end up here. You can see that there is PoCA here. So you have the code source that is here. You have released already some releases. And if you go here, you have the release 0.3, where you can download it here. There is already a very preliminary manual that is available on this version here. So it's pretty old already. I really need to put more effort on the manuals that will come at some point, but for now it's really preliminary, but that still you can download it. And if you download the zip, you can really basically take it here. So I downloaded it this morning, it's here, and you just dezip, and it should work directly, because it doesn't install any DLL in Windows or all this kind of stuff. Everything is which is needed is here. So still, you may find some problem with some missing DLL, but they are not linked to PoCA, and you have the result that is here. So sometimes Windows will ask you, will tell you that it's missing this DLL, for instance, and that means that you need to install Microsoft Visual C++ 2019 redistributable packages. So you can go here. Also, with PoCA, you really need to have the last driver of your graphic card, because some of the process are using the graphic card and the pretty recent extension of the graphic card. So you really need to be on the last version of your drivers when you are using 3D. If you are using PoCA for 3D, it's not true for 2D, but for 3D, you really need to have the last driver of your graphic card. And then when you have dezipped the archive of PoCA and installed the redistributable and the driver, you should be able to open PoCA and have this GUI. So we will see how it works later. For now, I will begin to really go inside my workshop. So I have a workshop that is more like hybrid courses and demo of PoCA. I'm not expecting you to do the same things that I'm doing, because I will need to go quite fast, and it's very difficult as on virtual, on remote, to have a proper workshop. So it's more like really I will try to teach you how people are quantifying single molecule localization data in the domain, show you how you can do that in PoCA, and then you will be able to test it at home when you want. So first, I will go with only one slide on what is single molecule localization microscopy. If it's okay. So this is a super resolution microscopy technique. Here you can see diffracted limited image. So all the fluorophore in the image are activated. And because of that, you have the diffraction limit of the light, and you have this diffraction limited image. In the case of the single molecule localization microscopy, we are able to only activate a sparse subset of the fluorophore at a given time. So you get this kind of result. So you can see that each one of the spots is diffracted limited, obviously, because of the optics. But now, because they are really sparse, we are able to precisely localize them with a process like Gaussian fitting, for instance. And because of that, we have the precise position of the molecules. And then we're able to use that in order to reconstruct a super resolution image that can have a resolution that down to tens of nanometers. But then, again, the difference is now we have coordinate in the space. We have the in 2D or 3D. So how can we use this localization, these coordinates, in order to do some quantification? Here you can see an image of a fibroblast that is expressing integrin beta 3 MEOS2. So this is a diffraction limited image. So basically, the adhesion site here are just a big stain. But now with single molecule localization microscopy, we can have this kind of data where we have a much better resolution in the adhesion site, and we can try really to use the localization in order to do our quantification. So first, what did people, when they had single molecule localization microscopy, did when it was released in 26? Basically, they went back to what they knew, which is images. But in this case, super resolution images, reconstructed super resolution images. So here you can see, for instance, the diffraction limited image with a pixel size of 160 nanometer because of the camera. If we go to this small square here, basically we don't see anything because of the diffraction limit and the poor pixel size. We do single molecule localization microscopy. So now we really have our localization with their 2D coordinates in this case. So here you can see the original pixel size, camera pixel size here. But what you can say now is that I will define a pixel size that is below this camera pixel size. So for instance, let's say that we are defining a pixel size of 20 nanometer. So now we have this grid, and we can project each localization inside each of these pixel, basically. And now the intensity will be the number of localization inside each of these super resolved pixel. So you can have this result here. Obviously, we can see that it's quite scarce because of the localizations that are scarce. So usually people were applying Gaussian on this localization, which sigma is defined by the uncertainty in localization, and you end up with this kind of result, which is smoother and easier to segment and quantify. The problem is that it can be quite complex to quantify pixel-based image. So here you have different kind of data. You have some virus here, you have some neuron, the adhesion site here, and some microtubule. And obviously, you won't be able to apply exactly the same technique in order to quantify this faux data here. So you will need to have some particular pipeline in order to segment particular logical model. But it's even it can be even difficult when you have only one data. So in this case, again, this fibroblast. But we can see that we have very different organization between the clusters that are in the adhesion site and the cluster in the background. So you will certainly need to change your pipeline in order to be able to segment the cluster in the adhesion site and the cluster in the background. Another problem is that obviously the pixel size that you will define may affect the quantification. You won't have the same image if you take a pixel size of 20 nanometer or 30 nanometer. So usually people are using the accuracy of the experiment. So let's say that you have a resolution of 25 nanometer in your experiment. They will use that in order to do the pixel size, but still it will change. If you change this size, your image will change. Also, the pixel dimension is fixed. So that means that you are oversampling sparser region because you will have a lot of pixels that will be empty, basically. And you are undersampling the denser one where some pixel will maybe have 1,000 in intensity. Center of localization inside this pixel. And usually when you are doing a pixel-based technique, you are using a combination of different techniques in order to do your analysis, and it may be complex to reproduce and generalize. So the question is, how can we use the pointillistic nature of single molecule localization microscopy data in order to help with the quantification? Because it's kind of sad to spend so much time to localize the molecules and then lose information by going back to an image. It's a discretization of something that is real, the coordinates, so it's losing information. So now really we have the localization, we have the coordinate in the space, so how can we use that in order to do the quantification? And it's very important because even when we are using the localization, there are it's complex to quantify because there are experimental parameters that will have an impact in the localization of data. So we have the experimental parameters such as the fluorophore photophysics. So different fluorophore won't have the same photophysics. That means that they won't have the same blinking, and one molecule will be defined by different number of localization. We have the labeling density, we have the acquisition time. So basically, that means that when you are doing a biological study, you will have data that will have very different localization density. So here you can see 4 data from the same experiment. Seems pretty much the same, but in fact, I have normalized all of the localization density with respect to the localization density of this data, which is the reason why it's one here. And here, it's almost 5 times more localization that's here. So obviously you don't have the same densities. That means that you need to have some techniques that are robust to density, to the localization density, in order to prevent yourself to change some parameter in order to do your segmentation. And you want something that is automatic when you are doing biological study. So in the field, people are usually using 2 families of technique in order to do quantification. They are using clustering or segmentation. So clustering is really trying to find clusters, but in a statistically manners. So you statistically characterize small aggregates of molecules, usually by comparison with a random distribution of the molecules. So we will go back on that and we'll explain more what it means. Or you can do some segmentation. So in this case, you are just trying to classify molecules in different classes with respect to some defined attributes, and techniques such as DBSCAN or Tesselation are using this kind of, are part of this family. So in a way, we can see clustering as one application of segmentation, because you cannot use clustering to do segmentation, but you can use segmentation in a way to do clustering, but clustering is still statistically relevant, which is not necessarily the case with segmentation. So if we go for clustering, the most used technique in the field is certainly the K-Ripley functions. So it's really trying to describe the average number of molecules that exist near another molecule within different radius R. And it does that by computing the deviation from a spatially uniform distribution. You do that by computing the K value for varying radius R. So the K function is this mathematical equation. So it's very easy. In the end, it just NP is computing the number of neighboring localization in a radius R. Here you divide by the average density, and then you do the sum of all, and you divide by the number of molecules. So it's really just trying to compute the deviation from a spatially uniform distribution. And that's possible because you know that in the case of a random distribution, the K value that you will expect for a radius R is PR square. The problem is that when you are using the K-Ripley, it's difficult to understand. You will see why when I will show you some the K-Ripley curve. So a lot of people are using the H-Ripley function, which is a normalization of the K-Ripley function. And in this case, you expect 0 at a given radius for a normal distribution. And H-Ripley is coming from K-Ripley with this equation. So here I will show a short animation in order that you better understand how it works. So you have here a data with some cluster, dataset with some cluster, and here you have a random distribution of the molecules. If we go to this small region, what you are going to do is that you will define iterative growing radius R in order to do your computation and compute the curve, the H curve. So you begin with a small radius, you compute the number of localization inside this radius for each of the localization on the dataset. Basically, that means that you compute a density value inside this radius R, and you will see that you have more a higher value for a clustered data than for a random data. So you have really here for this one, it's higher. You use a bigger radius. In this case, the value will go bigger, and the value for a random distribution will go around 0, as expected. You do that again for a bigger value of the radius, and in this case, it begins to fall. And here it keeps getting close to 0. If you do that for a lot of different R value, you end up with this kind of curve. So the one for the random keeps going around 0, and the one for clustered data will go up, reach a maximum, and then go back to some randomness. And in this case, the max is the radius of maximum aggregation in your data. So it will give you the radius of the cluster in your data. So it was used in a lot of different publications. Here you can see different data with bigger and bigger cluster. And when you put the H curve, you can see that this one, the red, which is this one, is the highest one, so has the bigger cluster. Also, they show that the width of the curve gives some indication of the relative density between the different data. But it's very heuristic. It's not mathematical defined. So if we go to this toy data, which are clustered in the background an adhesion site. It's the same, it's different part of the same data here. If we do the H curve on this one, we have a clear maximum around 100 and then it go back. And in this case here, we have something that has no maximum. And this is because in this case, here we have two levels of organization, background and cluster. And in this case, we have background, cluster, and adhesion site. So we have three levels of organization. And in this case, the replay curve won't manage to find the maximum radius of aggregation. So what is good with replay function is that they are intrinsically normalized. And it's very important because that means that you can use it exactly the same way with data that have different localization density. One of the limitations is that it gives only one value. So it's great if you only want one value, but you won't have, for instance, the distribution of the clusters, which may interest you. And it's also sensitive to multiple levels of organization, again. So that means that even if there is no user bias, because you just say, okay, I want to compute the curve between a radius of, let's say, 5 nanometer to 250 nanometer with step of 10 nanometer. So we cannot say that there is really user bias here. You just take a big frame and try to see if there is some radius of maximal aggregation. Usually people will use that in some ROI where there is only two levels of organization, or because it's it takes some time to compute, they will use ROI. And in a way, your bias comes from your choice of ROI, obviously. ROI, region of interest. Still, it's implemented in PoCA, so we will begin to do some playing with PoCA to show you how it works. I execute the software. So it opens this this data, this widget, sorry. I will just add a few data with simulation and a very simple cluster in the data folder. So you have different way to open data in PoCA. You can use this icon here, which is open file. It will open this dialog. You can go to the data. Let's say that I want to open these three data sets. So I do a multi-selection. I click on open, and every time you open a CSV, it will open this widget dialog, where you will be able to choose what you want to load or not. So it's important because you need to say to the software which column will be X, Y, and Z if you have. So here it's already directly decided because the header of the file was X, which is expected, and Y, which is expected. But it's important that the software expects X and Y. So if you have something that is called X nanometer, for instance, you will need to specifically say to the software that this is the X column. So in this case, we are fine. You can apply a calibration here. Let's say that you have your coordinate in the frame of the pixel camera. You will need to apply the calibration. So let's say it's 160 nanometer. For the XY, you will need to say, okay, this is 160 in order to have your coordinate in nanometer. And everything, if you have your coordinate in nanometer in PoCA, everything will be computed in nanometer, nanometer square, or nanometer cube. And it's better because you have direct result in the good calibration. So here I'm happy with this loading X, Y, intensity, and frame. So I say OK. Now this is for the second file, and this is for the third file. And here you have this icon here, which is tiling the window. So here, if I click here, it will tie the different window directly. So we can see that we have three different data sets which are basically exactly similar. It's, I think, 50 clusters, but with different density. So if we go to the tab localization here, we have a K-Ripley tab here. where you can define the mean radius, max radius, step radius, and compute the K-Ripley. So we'll go to this data. I compute the K-Ripley, and you can see that the K curve is just, you don't understand where is if there is some maximum aggregation or not here. So you can click on here. So I know I put L, but it should be H. So display the H function and H-Ripley. And you can see that in this case, we have a maximum radius of aggregation at 60 nanometers. So if we go to this data, we can also compute the K-Ripley H-Ripley function. So it's still computing here. And you see that you have exactly the same radius of maximum aggregation. And we will go to the last data, still compute the K-Ripley. It will be a little longer because there is more localization. But you will see that in the end, we will have the same result. So basically, we have exactly the same organization with just different density. So we have exactly the same result for the replay function. And that's really a strong point of the replay function, to be that robust to localization density. So it's close to be finished. And it's done. Almost. And you see that still we have the same radius of maximum aggregation. So this is really something that is very interesting with the replay function. But in the end, you still have only one value. So it's nice for relative analysis, but if you are interested in the distribution of your cluster, you cannot use that in order to have this kind of information. And so basically what you can do is use segmentation technique. So in the field, there is basically really two big families of segmentation techniques that are used. There is DBSCAN, which is, I think, by far the most used technique, which is for the density-based spatial clustering analysis with noise. So it's a segmentation technique. You can obviously segment object or cluster depending on your parameters. It organizes the localization with respect to density in three classes: core point, density reachable point, and outlier point, as you can see here. But I will have an animation after to show really how it works. It uses two parameters: the radius R, which is basically the neighborhood size in order to compute some value of density, and the mean points, which is the mean number of points in R to be a core point. And must be cautious, mean points is not the mean number of points of a cluster. But again, you will see why just after. And you can see here some of the toy data that were used in the original paper in order to do the segmentation. You see that you can really segment some very diverse shape, and it's working pretty well. So how does this technique work? So first you will define a mean point in order to be a core point. So let's say that it's 4. You are at this point, you have your R that is defined. You will compute the number of localization inside R. So here it's 5. 5 is lower than 4, so you have a core point here. You go to this point, it's only 2 points, but one of the points that is inside is a core point, so you call it a density reachable point. In this case, you have only 1 point, non-core point, so it's an outlier point. You do that for everything, and you end up with this classification: core point, density reachable point, so basically the border, and the outlier point. And usually in single molecule localization microscopy, we end up with 2 classes, because we say that the core point and the density reachable point are our objects. So it was used in a lot of paper, for instance, in this case, where you can see that they really managed to do some nice segmentation of, I think, protein in bacteria. And really, they had the distribution, so they could do a quantification of the number of protein per cluster, the number of cluster per chromosome, and the distribution and size of the cluster. So we go back now to our toy data. So in this case, let's say that we put a radius of 35 nanometer and a mean point of 15. In this case here, we have a density of the data of 400 molecules per micrometer square. And we end up with this segmentation, a pretty nice segmentation of the different clusters. Now we go to the adhesion site, which is part of the same data. But here, in this case, in this magnification, we have a density of 1,900 molecules per micrometer square, which means that when we do the segmentation, we end up segmenting the whole adhesion site and not the cluster inside the adhesion site. And if we want to segment these clusters, we need to change some parameter, but now we lose some of the cluster in the background. So DBSCAN is, in a way, easy to understand and use, but still it's two parameters. So when you use them, it's difficult because you can change any of these two parameters and have different results, and you can have the same result with two sets of parameters. So it's pretty difficult to really manage to use them if you are not an expert. And the biggest problem is that it's not normalized. So you use a radius, you don't have any normalization with the local density of your data. And that means that as soon as your density will change, you will need to change also your parameter. And that's a real problem, as you will see with this simple data here. So I also added DBSCAN to PoCA. So you have the tab DBSCAN in the tab localization here. And you have a few parameters here. So the distance, the radius R, the mean number of lock, which is the mean points in order to be a core point, and the mean number of lock in a cluster in order to really discard cluster with not enough localization. So if we go to this data and click on DBSCAN, I will just get rid of that. You can see that still it's a little too big for this data, so we need to do some modification of the parameter. Let's say we try that. Doesn't change a lot, so maybe 10. No, bad idea. So let's keep that. And let's see, well, we begin here. The segmentation is pretty nice. So we have this parameter here. If we apply the same here, we can see that already we have something very bad. Basically, he segmented a big object with everything and a few in the background. And I think that it will be even more bad if we do it here. You will segment everything, I think. Exactly. So you see that in order to be able to segment this data now, I will need to change some parameter. So I don't know, maybe I will need to put 35 here. Begins to be better, still a little too big, so you will need to go maybe like that. So you have two parameters, you can change the two parameters, you need to change every time that there is different density. So when you have your biological study, there is a lot of odds that the density will be different. So you will need to go check every one of your data to see if it's working or not. So it's a big problem, I think, with this technique, even if it's used a lot and it's working, but this problem of density is really annoying. The second family of techniques that is quite used in single molecule localization microscopy is tessellation-based techniques. So the first one that was used in the field was using Delaunay triangulation. So Delaunay triangulation is a space subdividing technique that is using triangles constructed from the molecule's coordinates. So if you have this data, you end up with this mesh, and you can see that there is no triangles that overlap between each other. So it's really by construction. And so now you can use the global definition of a cutting distance in order to create your object. So basically, that means that if you say that a cutting distance is 25 nanometer, you will discard from this mesh all the triangles that has at least one edge that is bigger than 25 nanometer, and then you will merge all the touching remaining triangles together. And it gives you this kind of segmentation. But that's the same that there is the same problem than for DBSCAN, is that it's not robust to density, meaning that if you apply this cutting distance to this data, you will end up with this segmentation where you don't manage to segment the small cluster. And if you change your cutting distance in order to be able to segment these clusters that are denser than the one in the background, you will lose the one in the background. Still, Delaunay triangulation is also available in PoCA. So if we remove the display of DBSCAN, go back and we can display the localization. You have here this icon, which is Delaunay triangulation. If you click on it, you end up with this Delaunay triangulation. You have the tab Delaunay that appears here. So you can see really the mesh in this case. You can do some translation by clicking on the middle button of the mouse. So in my case, it's a wheel. I click on it. If you go with the wheel up and down, you can zoom. You can also zoom by clicking on the switch and the left button. And then you can, again, apply the cutting distance. Say that you want all your cluster to have at least 10 localization. If you apply the distance, you end up with this. And then you can create your object if you want. Okay. So this is for the Delaunay. So again, as I said, it's not normalized, which is still a problem. And besides, the relation between the triangles and the localization is difficult to envision because one triangles link three localizations. So how can you use the triangle in order to add relevant features to the localization and add these features in order to do the segmentation? This is not easy to envision. And so what we decided to use in the team is a Voronoi diagram. So the Voronoi diagram is a dual of the Delaunay triangulation, meaning that you can construct one from the other. So if you have this localization here, you can do the Delaunay triangulation like that. And in fact, you can construct the Voronoi diagram that you can see here, these polygons, from the edge of the triangle. So obviously, the algorithm is a little more difficult than that, but you can see that, for instance, this one is a bisectrix of this triangle edge. So when you do that, you end up with this space subdividing technique, where you can see that any point in the space that is inside this polygon is closer to this localization than to any other localization. So as for Delaunay triangulation, Voronoi diagram is a space subdividing technique. It's anisotropic by nature because you don't have any radius. That's something that I forgot to say about DBSCAN or K-Ripley, but since you are using a radius, they are quite isotropic by nature, and it can have a result on your result in the end. And here you just care about the vicinity of your localization. And what is really, really interesting here is that you have one localization one polygon per localization. So you have a bijective representation of the localization, and that means that you can compute features on the polygon to add them to the localization. And Voronoi diagram has two really very interesting features. First, there is the connectivity. So you know the direct neighbors of one localization during by construction. That means that any polygon that share an edge, you see that these two polygons share an edge here. That means that these points are direct neighbors. And you know that by construction, and you can retrieve the direct neighbor during the quantification. And the second feature is the scalability, which is that the denser the localization are, the smaller the polygon will be, which is really interesting because that means that you will really take into account this when you compute some features on the polygons. And what we have done is that we, in the original paper, in the original SR Tesseler paper, is that we use that in order to compute statistics on the polygon and to generalize this computation in order to add some features to the localization. So let's say that we have this data here, this Voronoi diagram, and we have these features. So the polygon, a number of neighbors n, a polygon area A, and a local density delta. So if we are at the rank 0, meaning that we only care about this localization, the n0 is 1, the area of this polygon A0 is in yellow here, and the density delta 0 is 1 divided by this area. But now we can generalize that to rank 1, for instance. So we know that n1 is 5, current localization plus its direct neighbors, which is the number of 4. The area is the area in yellow and green, and the density is 5 divided by this full area. You can do that for the rank 2, and you add this result for the density and the area, and then you can do that for the rank k. In the end, what we mostly use is the rank 1, because with respect to rank 0, it has a smoothing effect, and we find it better to do segmentation. And here you can see that we computed the local density at the rank 1, and we colored each of the polygon with respect to its density. But something that is really, really interesting with the Voronoi diagram, and it's because of its connectivity and scalability, is that we managed to find a way to normalize it. So it's not a mathematical normalization, but still it's a kind of normalization that is working pretty well. So here you can see, in this case, it's two exact, it's the same data, but in this case, we have 5 more localization, but it's work if you have similar organization. And that's what you would expect if you are doing a biological study, that you have different density, different sample, but still some kind of organization in one of the conditions that you are imaging. So if you do the Voronoï diagram and you compute the rank 1 density, you end up with that result. So you can see that here it's the logarithmic distribution of the density. We have a shift distribution between the two, with this one being shifted to the right because it's denser. So if you are doing a simple thresholding, like here you can see that there is 2 populations, it's a very easy data to see. You can put a threshold here, we manage to do a nice segmentation of the cluster. But if you put exactly the same threshold in the denser data set, you will end up with this crappy segmentation where you begin to segment basically the background also. But what you can do is that you divide the local density by the average density of your data. So basically, it's the number of localization divided by the area of the data. When you do that with these 2 data, you can see that now the frame of the 2 distribution is the same. And if you apply the threshold here, which is 0, meaning 1 times the average density, you end up with this segmentation. And if you apply the same in the denser data, you end up with this segmentation. So you basically are able to apply the same threshold in the 2 data, which has a different localization density. So that's a way to use normalization. There is other way to do normalization in order to go back to more statistical computation of the clustering. It was done by a team in Strasbourg in 2016. So we used normalization and thresholding, they used normalization and Monte Carlo simulation in order to do clustering. And the idea here is that you have your experimental data. So here it's a simulation with some cluster. You have unlocalization in some area. You will generate n K simulation. So let's say 500 simulation of a random distribution of the same number of localization in the same area. You compute the Voronoï diagram, and you plot the area, the polygon area. So here you have this experimental distribution. In the case of the distribution of the random distribution of localization, you can see that the distribution is different. In the end, you plot the experimental distribution and the mean of the distribution of the simulation. And when you apply this threshold where they cross, you end up with this segmentation. So you manage to statistically find a correct value in order to do the clustering, to identify the cluster in your data. Obviously, it won't work in this case because you don't have cluster, so it's really good for clustering, not for segmentation. And here, when you apply what we have shown with the Voronoi normalization applying a threshold, you may end up with this kind of nice segmentation of the microtubule. So let's go to our toy datasets with some cluster in the background and the adhesion site. We compute the Voronoi diagram. We compute the density. We apply a factor of 2, let's say, and we end up with this selection of the Voronoi cells. We can create some object, and then you will say, okay, but you have exactly the same problem than with DBSCAN, because now we segmented the whole adhesion site and not the cluster inside the adhesion site. That's true, but the difference is that we can use exactly the same techniques that we show here inside the adhesion site. So we can choose the localization that have average density twice as average density of the adhesion site here in order to find this selection of cluster inside the adhesion site and create the object, the cluster. And now we have cluster inside the adjacent site and outside. And we have a workflow which is very clear, which is applying twice the average density here and applying twice the average density inside the adjacent site in order to find the cluster. And you can apply that in all your data and you don't care about the localization density of your data. So a word of how are we quantifying the size of the segmented object, because now we managed to do some segmentation, we have some object, but how can we compute the size? Because the number of localization is easy to find since we did the segmentation, but we need also to have an idea of the size. So there are basically 3 ways to compute the size. Either you compute the area because you have the outline of your object, so you can compute the area. You can fit a bounding ellipse. The problem is that it kind of overestimates the size, so it's never used. Or you can do a principal component analysis. So basically, you have the point of your object. You will do a linear regression in order to fit a line that best describe your the object localization. You find the centroid. You can compute the perpendicular frame here, and then you will take each one of your localization and project to the 2 line. So you will have a distance in y and a distance in x for each of the localization. You do the distribution for x and for y, and for z if you have a 3rd dimension. You find the standard deviation and you multiply by 2.35. So we are doing that in order to do to find a similar way to compute the size that the one that were computed from reconstructed super resolution images. Because when people are using reconstructed super resolution imaging, they are using pixel-based thresholding in order to find the object. And then when they have the cluster, they fit a Gaussian on it and they take the full width at half maximum of the Gaussian. So basically 2.35 of the standard deviation of the Gaussian. So we are doing the same with the localization in order to have something, some similar size of the object that you are quantifying with the localization. So between using the area of the principal component analysis, I would say that use the one that is used in your domain. So if in your domain they are using area, use the area. If they are using size, use the principal component analysis. And here you can see the multiscale segmentation that I explained here on the whole data, where you can see that every cluster in the background and in the adjacent site were segmented, and that we find that there were different cluster size and density between the background and between the ones in the adjacent site. So now I will go back to PoCA. I will close everything because it begins to be little crowded. So this is this icon here that will close every data. I will go back to opening the 4 data. So you show that we can do multi-selection in the widget, but you can also do drag and drop. So you have the 3 files selected and you drop them in the widget of PoCA, and then you are able to load them directly. I'm doing the tile again, and then here I will go to this icon here, which is a Voronoï diagram icon. And then I will create them for the 3 data. I will get rid of showing the localization, go to the Voronoï tab here. So you have computed here the area and the density. I will go to a logarithmic distribution, which is when you tick this box here. Here, this is a logarithmic distribution of the density, and you have a better idea of how it is distributed now in logarithmic distribution. You can do that for the tree. And then I will get rid of the display of the point in the Voronoï diagram to have a better visualization also. And I will get rid of the cut distance. I don't want right now. I will put a factor of 2. So it will apply 2 times the average density as a factor for the thresholding. And you end up with that, and that. And then I can use this button here to create the object. I create object, and I create the object. And if I go to the object list tab, which is here now, you will see that you have the distribution of all your objects segmented with the area, the ID, the number of localization, and the size. We have 50 cluster, we have 50 cluster, and we have 50 cluster. And obviously the number of localization is different because of the different density. So I will just close this one and this one. So you have a few things that you can do with PoCA. I will get rid of the object for now and of the Voronoï, go really to the localization. So I show you the DBSCAN and the K-Ripley. You have also a few things that you can do directly on the filtering display of the localization. So first, you can do some filtering by going directly to the histogram of your features. So here it's X, Y. Here we don't see, but it's intensity, and here it's frame. So only one frame since it's a simulation. So you can do some filtering if you want, like that. If you create a Voronoi diagram, it will still keep all the localization, even the ones that you filtered. But when you have done some filtering, you can go to this button icon here, and it will duplicate the data, the filtered data. So if you go here, you can see that this part here is really this part here. So you filtered your data, And then you can do the Voronoï here if you want, or the analysis on this data that was duplicated. Okay. Here, this is a different way to display the data. So first, you can change the features that you will display by going to this target button. So here, this is the X features that is displayed, as we can see here. If you go here, you will say this is the Y. So now you really see the LUT is applied in the Y coordinate of your localization. You can select the intensity of the frame, but there is the only one here in this case. You can save the value of the histogram with this button. If you put some value in the text box, it will update the histogram. And here, this is in order to remove the features. So you cannot remove X, Y, and Z features because they are always needed by the software. But you can remove, for instance, the intensity if you don't want. And you have no intensity features anymore. Here, this is in order to display bigger or smaller point. Here, this is in order to display the localization as a heat map. In this case, radius is a little big. So you can see that you have a different, it's really an heat map, so you can change the LUT and play on the alpha or the radius of your heat map in order to have a different visualization. And this one is Gaussian, but I will show it in 3D as it's better in 3D. And here, yes, you can change the LUT that you apply directly on clicking on the button that shows the LUT that would be displayed. So this is what you get with the filtered display localization tab. For the Voronoï, you already seen. You can also display point with the Voronoï density here. So here you can get rid of the polygon of the Voronoï polygon, and you can see here only the point and the point with the density. You can also show the outline of the cell with this button instead of they being filled. You can invert the selection if you want with this button. If you apply a filtering like that and you go to create object, it will use the current your current thresholding basically. And this thing is still ongoing, but it's basically the implementation of the technique I show you from the guys from Strasbourg in order to do clustering with Voronoi. So it does some simulation in the background, find the two lines, the two distribution where they cross, and applies thresholding in order to do clustering. That you can see that it's still ongoing since it doesn't show the curve well it should. So it's still ongoing. You can create a few ROI if you want. So let's say that you want to create this ROI, this one, and this one. If you go to the creation of the object and you say in ROI, and you create again your object, now the object were only created inside the ROI that you define. And here you can see that it will give you the type of the ROI, the area of the ROI, and also the perimeter of the ROI. And then you can save the ROI, you can load them. and you can discard some selected ROI or discard all, for instance. Here you have very common setup, but I will show them also in 3D as it works better. And yeah, let's test in 3D just to show you. So here I have this. So in this case, you can see that what we didn't have before is that in the required column, it says that X is not selected and Y is not selected. And that's because exactly what I said before is that in this case, the header here is X X. So it's not X alone, and the software doesn't know that it's the X column. So you need to go to this list and select X here, select Y and select Z. So now we are happy, we can say OK, and you have selected and loaded your data in 3D. So in this case, you can see that the simulation I have done is pretty bad because there is a lot of space where there is no cluster. So you can do some very fast cropping first, but it's only for visualization. So let's say that you want to go to some cluster. You have the choice of the 3 frame, XY, XZ, YZ. So you choose the frame, it will go directly on this rotation, and then you can select the cropping tool. Now with the mouse, you left click and stay clicked, and then you drag drop until where you are happy, and you release the button, and you will directly crop your data. And then you can go to this XZ frame, do exactly the same thing. And then if you click on XZ again, it will release the crop button and release the blocking of the rotation. And then you can really have directly a cropping of your data, very easy in order to go to some specific part of your data. Here, this is the button in order to reset the cropping. And you are back to the whole data. So let's say that here I'm not happy with this fact that there is this whole empty space here. We can see that it is in the Z direction. So we go to the localization tab, we go to the Z, and we can see that indeed here there is almost no localization. So that's this part. We apply some thresholding, and then we can do the duplicate. So now indeed I get rid of all this blank space. I can close that and go here. So one of the things that is possible in PoCA is that you can play with the size of the localization if you want, do some cropping again in order to go only to one localization, one cluster, sorry. And you can, for instance, if you want, add some ambient screen space, ambient occlusion. Here you can see that it will add some shading in order to have a better understanding of how is our cluster. So in this case, I just put a big point in order to show how it works, but you can also do it in smaller point. It really helps with the shading in order to have a better understanding of how our localization are with respect to each other. It's only visual, obviously. Here you have the bounding box of your object. So in this case, it's not the bounding box because it's related to the cropping that I have done. And you have this grid that will give you an idea of the size of your current grid here. So it starts to 0, it go to something like 230 nanometers, certainly, even in this case. And then you can change the number of grid that you want. So either by number, so let's say that you want 10 and you have put isotropic definition here. So we will put 10 ticks here. You can put it with respect to the length. So here it would take it every 50 nanometer. You can choose to not have something that is isotropic. So maybe you want 20 nanometer in D. Put it in the, in the Z axis here. So you have a lot of things that you can do here in order to have a direct idea of the size of what you are analyzing right now. You can save some camera position and load it. So let's say that you want to save this camera position. And then you go back to that. If you save it and load it back, oh, maybe it won't work. Oh, it didn't work. So for now, I guess that loading and saving and loading the camera position is not a good idea. I guess I must have changed something and I broke something else. But it will work at some point. Let's go back to the data. Crop again. No, that's not what I wanted to do. Sorry. I wanted to do some filtering. Up. Duplicating and getting rid of this one. So this is not working right now. You can change the background of your data if you want. You can create some Voronoï in 3D. So here you have some option for the plugin. You can go to the parameter. In this case, I will say that I want to create the cells, which is not mandatory. So in the Voronoi diagram, some cells are created, but they are not passed along to the CPU. That means that when you want to create cells, it will be done after the creation of the Voronoi diagram on the CPU. And this is something that takes quite some time for bigger data sets. But let's say here it's not a lot of data, so we can say, okay, I want to create the cell just to show you that it's really working, and create the Voronoi diagram. And I end up with that. So I go to the Voronoi tab, put the logarithmic distribution, and do some filtering, and you can really see that we have created the Voronoi polytope in 3D, polyhedron in 3D. And then you can again do some segmentation in 3D in order to have your object directly. So when you have your object, here we'll get rid again. As for Voronoi diagram, when you have your object, you also can display the localization that are part of the object. That's here. So either all the points or only the point in the border. So here you have your surface and volume of your object. When you go to an object, you can see that you have some information about the object that is displayed here. It's also true for the Delaunay triangulation, for the Voronoi diagram, the localization. So you have the object ID and all the features that were computed. So the major axis, minor axis, the second minor axis, because it's in 3D, so there is 3 axes, the number of localization, the size, which is basically the major axis plus the minor 2 divided by 3, the surface, and the volume. So when you are on an object like that, you can click on the right button, and you can see that it's saving your object with the current rotation. So you can do that, and then if you click on this image, it will directly go back to the object, so zoom to the object on the rotation that you have saved. So So it's really helping to choose some object and to go back to this object in order to see how they are. So then you can go back to this button in order to reset the view. For the object, you have also, again, the possibility to change the LUT. You have the possibility to filter. You have also a high-low rendering, where you will render in magenta all the objects that are not selected and in grid the objects that are selected. So it can be interesting in order to see the organization of some object with respect to the other if you are interested. When you click back to another LUT, we'll go back to the normal visualization of the LUT. If you go to an object that is picked like that and you double click on it, it will also go directly to see to this object in order to see how it is. When you go to an object here, it also go directly on this object on the list here to show you where it is. And here you have a few things like you can duplicate the centroids of your object. So in this case, it would give you that. You can select some object and duplicate the localization of these objects. So in this case, I had only one object that was selected. But if I go here and I select a few, like that, and I duplicate them, it will duplicate the full selection. When you do that, you see that you have lost the picking possibilities of your object. So you need to go back to this button here that allow the picking. And here it's in order to save the state of the object, so this list here, or to save the localization of the object. So something that you could also do by doing that, exporting, and then going to the localization and saving the localization here. So that's a different way to do the same thing. Okay. So it's what I wanted to show right now. One of the last thing I want to show right now, and then I will go to colocalization analysis, is that I will go here, open only one data. So let's say this one. Again, I'm choosing X, Y, Z. I'm creating a Delaunay triangulation in 3D. Here, I'm applying a cutting distance and a mean number of points of 10. And I'm creating the object. So I have done a full, let's say, pipeline, opening the data, creating the Delaunay triangulation, creating sub-object. In PoCA, every one of these commands is handled as a JSON file. So JSON file are files that are used in on the web, and they are human readable. So you can very easily read what it is. And that means that now I'm also able to record every one of these actions that are performed. So in this case, it's here I have opened some data. I have done a few things like clicking on the button, and that's what we see here. But this is opening the file, creating the Delaunay, creating the object. Now changing the parameter, applying the cutting distance, and then creating the object here. So I can take every one of these actions, paste it here. We'll just get rid of that don't have any interest. This one was just going to log display. and I will change the name here. So this was Colloq Test 3D Simulation 1. So we'll put Colloq Test 3D Simulation 2 and run it. And you can see that this is now Colloq Tesseler Simulation 2. The Delaunay was created and the object was created. So basically, every one of the commands of PoCA is recordable, except if I have some bug, but everything should be recordable. So that means when you are done with your pipeline and you are happy with it, you should be able to save it and then to apply it to new data directly. And that's one of the things that I wanted to be able to do. That's creating, defining a workflow and then just clicking on a button and it will apply the workflow on all the data that you have acquired. And now I will go to colocalization analysis. So we have 10 minutes. It will be a little short, I think, but let's go. Colocalization analysis in fluorescence microscopy, the two gold standards that are used with common fluorescence microscopy is Pearson correlation coefficient and Menders coefficient. So one is an indicator and one is a quantifier. So basically, you have your two labels. You have the same image. That means that one pixel corresponds to another pixel in the other image, and that you can do some correlation analysis or colocalization analysis between the intensity of the two pixels in the two images. Because this pixel here corresponds to this pixel in the other label. So in the case of the Pearson correlation, you will try to find some correlation in the intensity between the two channels. When you do that for all the data, all the pixels in your data, you end up with this kind of scatter plot. And depending on how it fits, it's not really fitting, but let's say how the scatter plot is showing a direction, we'll know that it's either exclusion if it's go down, not correlated if it's around 0, or highly correlated when it goes to 1. In the case of the Menders, what you are going to do is first you need to do some segmentation, and then you will compute the overlap of your segmentation, and it will give you a value of the overlap, a quantified value of the overlap. So in this case, obviously, the Menders coefficient of the green label is bigger because there is only one object that is highly colocalized, while for the magenta label, there is two objects, only one is colocalized. So it explains why you have these differences in the two value for the Menders 1 and the Menders 2. So they are really the gold standard in fluorescence microscopy because they are easy to use and easy to understand. But now we have localization, so we don't have this kind of direct link between one point that is in a real space and the other point that is also in the real space. So they shouldn't be at the exact same space, so you cannot link them directly together. So if you want to do some colocalization analysis, you can do object-based colocalization or unorganized neighboring, or you can use unorganized neighboring techniques like K-Ripley, but bivariate K-Ripley, for instance, or bivariate unorganized neighboring techniques. So in the case of object-based colocalization, you are going to try to find the overlap between the segmented object and compute the colocalization as the overlap. So obviously it will depend heavily on the quality of the segmentation. It also don't really take into account the spatial distribution if you create your object on the border. Like here you have different density, it doesn't really take that into account when you do the overlap. So maybe it's a problem, maybe it's not. Yes, it will really depend on what quantifier, what indicator you're interested in. So for the unorganized neighboring technique, there is, for instance, the Gettys and Franklin method, which is pretty similar to K-Ripley, where you define a radius. You will compute some kind of density based on this equation in your color and in the other color. Then you will do a scatter plot and you will apply a threshold in order to find the colocalized region. So it's working pretty well, but what we saw is that it's not as robust as K-Ripley to density, so you usually need to change the thresholding if you have very, very different ratio. There is also the coordinate-based colocalization, where again, you will define a radius, but also a number of bin. So in this case, you will compute the localization in the two color, but in rings. So first ring is this one, so it's a circle in this case, but then you will compute in this ring, in this ring, in this ring, and in this ring. So you have this number for each of the ring, gives you this kind of distribution. You will find, like for the Pearson coefficient, how is your curve, and it gives you a coefficient. So still, there is a difference with the Pearson correlation. The Spearman rank correlation is done on the rank in order to not have a linear, the necessity of linearity between your two staining. And that means that here you can see that it's the absolute value that was computed, the number of localization here. And what you are taking in order to do that, it's not this value, but it's the rank of this value. So let's say that you have this distribution, you do the sorting, and you will take the ranking. So the first is the first, obviously, but then the second in this sorted distribution is third. So this is the second one in the distribution. This is the third one, and then fourth and fifth. And this is the rank that you will compare in order to compute the Spearman rank correlation. So you can clearly see that you don't need some linearity between these two values, since this is this value that you compare, the rank. And it's really necessary with single molecule localization microscopy because of the difference in the localization density in your two staining. Same as for Pearson, in the end, you will have this curve that will say that if you are excluded, not correlated, or correlated. So it's also working pretty well. You can display the distribution of your coordinate-based coefficient, and you can apply a threshold in order to find the colocalized localization. Still, you can see that it's again two parameters as for DBSCAN, so it can be difficult to use them in order to have some kind of a good result. And also, the way they computed the percentage of colocalization is the number of localization that I hire to some threshold divided by the number of localization, which means that in this case, you have a bigger colocalization here than here. Why it is exactly the same data, but here with more noise. So that can be a problem. And because of this problem, there was CloudDot that was released a few years later. That is a combination of the density-based DBSCAN and the CBC. So I explained the two, I won't explain them again. CloudDot is doing exactly a CBC, but now inside the segmentation that is provided by DBSCAN. So you limit the colocalization analysis to the clusters, which is a good idea, but still you are using DBSCAN, CBC, and a threshold, so you have 5 parameters. That's a lot of parameters. And you have the problem of DBSCAN not being robust to the local density. So if you have different local density of your data, average density, sorry, of your data, you will need to change the DBSCAN parameter. So again, we have the gold standard in fluorescence microscopy, Pearson coefficient, Manders coefficient. Colocalization of multicolor single molecule localization microscopy can be difficult because it's not that robust to density, and you may have a lot of parameters. And what we wanted to do is to be able to adapt the Pearson and Manders coefficient to single molecule localization microscopy with something that would be robust to variabilities. And our this was to use the Voronoï cells as a proxy for the pixels. So from this data, for instance, we have two staining, so we have two Voronoï diagrams. We wanted to be able to end up with this kind of colocalization analysis. With in blue and red, you have the highly colocalized region. In yellow and cyan, you have the high density in only one color, and in black, there is a background. And if we go to this very simple simulation, we do the two Voronoi diagram. We could do some apply a threshold in order to see what object we will do, but that's not what we want to do here. And if you go to this point, obviously it's very easy to know that it's inside this polygon because it's its polygon. But in the end, it's easy to find in the other color because this point is inside this polygon. That means that this point here has a high density in the red channel and a low density in the green channel. And now you can add this pair density descriptor to each of the localization. So if you go to this point, low density in red, low density in green. If you go to this point, high density in both. So you do this scatter plot for all the localization, you end up with that. Obviously, you can separate the two color to have this two scatter plot, and then we can apply a threshold as robust that I show with other Tesseler for the segmentation in order to classify our different localization. And now we can compute the Mendel's coefficient of the color of the staining A as the density of the localization in red divided by the density of the localization in red and in yellow, and for the color B as blue and cyan. And we end up from this data with this result where we can really see where we have the colocalization, where we have the colocalized localization, and we can compute some Mendel's coefficient in order to find a real quantification of this colocalization. And here you can see that we applied it on some data from our collaborators, whereas I already published this data in a precedent paper, but in this case, they use reconstructed super resolution images in order to do the analysis and a pretty complicated workflow. And in this case, I only applied average density, a threshold of 1 times average density. And I click on the button, it did all the analysis, and then I just needed to put everything in the same plot. So we are done. I will just show you very fast that Colloc Tesseler is also in PoCA. So I'm opening these two data in 3D. Sorry. Like that. Okay, I have the two data. I go to this button that is a way to link the different data all together. So you can see that you can put 4 data for now, but the colocalization analysis will be only done on these 2. For the other 2, it's more like for visualization. So now you have the 2 data here. You cannot see really where is the first staining and the other, but you can very easily switch between the different color with these 2 buttons. And if you go to the localization, you can say, okay, I am applying, please. Okay, I don't know why it crashed. Let's test again, because I really don't understand. I tested just before, it should have worked. It's weird. Maybe I will end on a bug. That's sad, but you never know. Okay, I'm doing that. And okay, it's working now. I don't know. So you can very easily switch between the 2 color in order to understand where are your 2 staining. And here you need to create the Voronoï diagram for the 2 color. So create for the first, create for the second. I will get rid of the display of the Voronoï diagram. And now you can use this icon here, which is Colloc Tesseler computation. I will get rid of the localization display. Now you have a tab colocalization here, and you can see that you have the scatter plot, and you can apply a factor, and it will compute the Spearman. I didn't explain Spearman, but it's basically just applying a Spearman rank correlation on all the localization of your data. So there is no threshold that is applied here. It's really correlation between the all localization in the 2 color. And here there is a Mendel's where I applied this thing. So you have also access to Colloc Tesseler. And the last thing I want to show, which is really on the going, so not available right now on the GitHub, but now PoCA is a plugin architecture. So I have done something in order to compute the object localization. So I put this plugin in the plugin section. I add that. I will just open again the two data in 3D, and that would be, I will end up with that. So it will be pretty fast. Okay, I have my two objects, my two data. I create Voronoï. I create Voronoï. I'm going to create now some object. Là. Oh, yes, okay, sorry. Okay, now it's done. Here I will create some object. So I have my object. I will get rid of that, get rid of displaying the localization. I think I have the Voronoï. Okay, here I don't have the Voronoï. Don't display that, and I don't display that. Okay, so I have my two objects. I create colocalization object. I will go to change the LUT for my two objects, and now I have this icon that is object colocalization. I go here. If I go to this object, for instance, and I will put it on wireframe, you can see that now I have the colocalization that is identified. And here I have all my colocalization object. So this part, so I have 20 because I had 20 cluster in the two. And I have my whole distribution with the size and all this kind of stuff. You can very easily go to some object to see how it is colocalized. So it's still a little ongoing because I need to really put it perfectly, but you can see that it's working already pretty well for object colocalization. And I will end up on that. Thank you for your attention. Don't know if you have question. Thanks, Alex. Yes, it's for free. So you have it's on my GitHub. So F-Levet. You have PoCA, as you can see. You have the code source. So for now, there is only release, so installer for Windows, because I'm only developing in Windows, so I don't have a Mac. But you have the code source, and in the code source, I have put some CMake list, so it should help with the compilation. PoCA should be agnostic to Windows. So I really try to not have Windows specific function. It's using Qt, it's using things that are also ported for Mac and for Linux. So it should be able to compile. I'm not sure 100% because I never tried. Yeah, sure. Yeah, you can contact me if there is some problem. I always try to by email. So by email, it should be somewhere. I think that if you do a search for me, you will have, yeah, you can contact me here, or I will receive with this email, for instance. So pretty easy to find my email. It's best is email. I am also on the forum, image forum with Tesseler, but I just can't get any alert when someone send me something, so I usually don't go there so much. So email is best for sure. I don't know if anyone has some question, or otherwise you can say that it's good. We are done.